The 15-16, we're going to talk today about instantaneous velocity. Okay, so velocity is the rate of change in the distance with respect to the rate of change with time. So velocity will tell us how fast something is going, and it will also tell us which direction it's going. So if it's positive, it moves up or to the right, and if it's negative, it moves down or it moves to the left. Okay? So our first question, displacement S in meters of the particle moving in a straight line is given by that function where t is time measured in seconds. Determine the average velocity between 1 and 3 seconds. So I want to figure out on average how fast this particle is moving. So to figure out on average how fast it's moving, I need to figure out the change in the displacement and divide it by the change in the time. Because that will give me a rate of change. So to figure out the change in the displacement, I need to figure out where the particle was at 3 seconds. In order to do that, I take 3 and plug it into the displacement function. Subtract off where the particle was at 1 second, because the difference between them will be the difference in the displacement. Does that make sense? And then I divide it by the change in the time. So stopped at 3 seconds, started at 1 second, so 3 minus 1. So to figure out where the particle was at 3 seconds, I substitute 3 into the displacement formula, so 3 squared plus 2 times 3. Subtract off the displacement at 1 second, it should be 1 squared plus 2 times 1. All of that is over 2 because 3 minus 1 is 2. Do some math, and in doing math, proper bed mass, simplifying, you should get 6. Whenever you are dealing with the rate of change, always look to see if there's units associated with the question, which in this case there are. So what would the final units be for this rate of change? Okay. Good. Okay, so the displacement is measured in meters. The time is measured in seconds. So this particle on average is moving at 6 meters per second. Okay? So this tells me that it's either, because it moves in a straight line, so it's either moving to the right or it's moving upwards. Because it's positive, and that tells me how fast it's going. Any questions on average velocity? Okay, so it's the exact same thing we did on Monday, except we called it average rate of change. But when you're dealing with the rate of change in the displacement or the distance divided by time, then we call it velocity. And what's the difference between speed and velocity again? Anybody remember? Yep. All right, what does that mean? Maybe people don't know what scaling means. Right, exactly. Speed tells you how fast it's going. Velocity tells you how fast and which direction it's going. Okay. So I use that example for average velocity with me going home. I think I did with this class anyway. So I can measure how far my house is from here, measure how long it takes me to get home, and figure out on average how fast I was moving. But you know, when I drive my car, I'm going to have to stop for red lights, and I'm going to have to stop for traffic. Okay? So if I say I get behind and I start to speed, and a cop catches me on the radar, he's catching my instantaneous velocity, how fast I'm moving at that particular moment in time. So that's what we're going to be doing in today's lesson. Because we are going to be able to determine the instantaneous velocity. So how fast something is moving at a particular moment in time. So determine the instantaneous velocity at 2 seconds. So the instantaneous velocity happens at a particular moment in time. So we are going to determine the instantaneous velocity. We can't figure out the exact instantaneous velocity. In this course, the only thing we can do is estimate it. Okay? For those taking calculus next semester, you'll learn a method to figure out the exact value of the instantaneous velocity. Okay? So the velocity is a rate of change. In order to figure out a rate of change, I need to figure out the change in the dependent variable, which was the displacement, over the change in the independent variable. So to figure out a change in, I'm going to need 2 values. The problem with this is I only have 1 value. So what I'm going to do is I'm going to estimate the instantaneous rate of change by doing a bunch of different average rates of change. So I'm going to figure out the change in the displacement. I'm going to figure out the change in the time. And then I'm going to take the change in the displacement over the change in the time to give me an estimation of the instantaneous velocity. Okay? Because I need a starting point and an ending point, okay, what I'm really doing is I'm finding the average velocity. So I want to estimate the instantaneous velocity at 2 seconds. So I'm going to start at 2 seconds, but I'm going to end it very quickly. So I'm going to go from 2 seconds to 2.1 seconds. And I'm going to figure out the average velocity between 2 seconds and 2.1 seconds, because the time interval between 2 and 2.1 is pretty short, right? So it's going to give me a pretty good estimate of how fast it was moving at 2 seconds. You guys understand what I mean by that? Okay, so again, I can't figure out exactly at 2, so I need to have another time interval. So I choose 2.1. Now I figure out the change in the displacement, just like I did before, substituting these values in. And if you do that, you'll get 0.61. The change in the time would be 2.1 minus 0.1. Oh, excuse me, minus 2, sorry, right off. Minus 2. And then I divide out the change in the displacement divided by the change in the time, which works out to be 6.1. So on average, the particle is moving at 6.1 meters per second between 2 and 2.1 seconds. So I can say 2 to 2.1 is pretty close. It's a pretty short interval. So I can say the instantaneous rate of change is approximately equal to 6.1. How do you think I can get a better estimation of my instantaneous rate of change? Sure.
Smaller.
Exactly. If I make that time interval smaller, then I'm going to get a better estimation. So we're going to go from 2 to 2.01. What I've done now is I've made that time interval between 2 and the next value even smaller. So I'm getting a better estimation. So I plug this all into my calculator. And again, some people have a calculator where you can type everything in and get the answer. I don't care how you get the answer, as long as you write down the answer. Okay, so you don't have to show me any work or anything like that. You can just write that down. Okay, but remember, how am I getting that? I'm getting that by substituting 2.01 into the function and subtracting off 2 into the function. Then I take 2.01, subtract off 2, which would be that. Then I divide the first one by the second one, and I get that. So I get 6.01. So I'm getting a better estimation of how fast that particle is moving exactly at 2 seconds. I want a better estimation. What do you think I'm going to do? How? Right, use a smaller interval. So I'm going to use 2.001. Substituting that in, doing some work. So again, there's a lot of work required to get this answer here. You're plugging 2.001 into the function, subtracting off 2 plugged into the function, you get that as an answer. Then subtracting the time, you get that. Then dividing, you get that. Okay, so that gives me an even better estimation, because now I've taken the time interval and made it much, much smaller. If I want a better estimation, what would I do? Make it even smaller. And I keep doing that forever, and that's what calculus is. Calculus is the rate of change, and we take the limiting value of these average secant lines. So you'd be like, what's he talking about? You don't need to know that unless you're taking calculus, and I'll do a lesson on it for those who are in my class. But for figuring out the instantaneous rate of change, I just want you to do these 3 values. You're always going to do 0.1, 0.01, 0.001. The guide has you do a lot more calculations. You don't have to do it. Okay? So then you're just going to use the final answer here as your estimated instantaneous rate of change. So to write it, to make it look nice, you would write the change in the displacement over the change in the time, exactly when the time is equal to 2 seconds, was approximately equal to 6 meters squared per second. Okay, because you can see that if I make the time interval even smaller, this would get closer to 6. If I made it even smaller, get even closer to 6. Okay? So the point of calculus is we make the time interval between them so small that essentially there's no difference between them. Okay, and that's called limits for anybody going on calculus. Rebecca, you don't think you wanted to ask me? That's just notation. All this is saying is this value when t is equal to 2. That's just mathematical notation. Okay? Any questions on that? So basically, this is the essential part of the guide. This is it. Nick, are you going to ask something? You just when you're asked to find the average velocity, you're going to be given a starting point and an ending point. You use your slope formula once. If they ask you to determine the instantaneous velocity, right, or instantaneous rate of change, you're going to be given one value, and you can't figure out it without having another value, so you do this interval chart. Okay? If you understand this, you pretty much understand most of the guide. Okay? So let's try this question right here. The population of a bacterial culture after T hours is given by that function. Determine the rate of growth at 5 hours. So the first part is this a instantaneous velocity question? Not velocity, I shouldn't say velocity. Instantaneous rate of change or an average rate of change question? And how do you know?
Sure. Instantaneous.
How do you know that?
Because it doesn't have 5 hours.
Exactly. They only give you one value. So as soon as they give you one value, you think, okay, I have to do an interval chart. Right? Because the only thing I can do now is estimate that instantaneous rate of change. Okay, so use the variables associated with the question. I want to figure out the change in the population, which is n, with respect to time. So you want to figure out the change in the population divided by the change in the time, and that will give me the change in the population with respect to the change in the time. What's my first interval I'm going to use? Because I'm trying to figure out how the population is changing at 5 seconds. So what's my first interval? All right. Perfect. All right. 5.1. Because I want the difference between my starting point and my ending point only to differ by 0.1. Okay. I substitute 5.1 into the population formula, subtract off 5, substitute into the population formula. I do some math, and if you do your math correctly, you should get 32.12. Then I figure out the change in the time, which is 5.1 subtract 5, which is 0.1. I divide these guys, and that gives me my first estimation of how the population is changing exactly at 5 hours. Okay? So the average change in the population between 5 and 5.1 is 321.2 bacteria per hour. I want a better estimation, I close that interval. And again, on your test, you're only, oops, I went too far. You're only required to do these 3. So the next one would be 5 to 5.01. You figure out that. And then the last one is 5 to 5.00. So every single time you're asked to figure out the instantaneous rate of change at a particular point, you're going to write down that point, and then you're going to write down that point with 0.1, then 0.01, and 0.00. Okay? Any questions? The textbook and the guide has you do a lot more calculations, and it has you do it on the other side. Because I can pick numbers, I could pick like 4.9 to 5, and 4.99 to 5, and 4.99 to 5, give me the same answer. But they have you do it on both sides. I don't expect you to do that. Okay? I do expect you to do 3 of them. Don't just do this final one, get the answer, because essentially we're just using this answer here. Okay? But I want to see this. So then, the rest of it, right, you don't have to show how you get your answers. You can just substitute them into your chart. Okay. Oops, there's a 0 here. you can see as I close my time interval smaller and smaller, it looks like the change in the population is 320 bacteria per hour. So the change in the population with respect to the change in the time, exactly when the time is 5 hours, is approximately equal to 320 bacteria per
This is just sort of like a estimate answer.
Yeah.
Always going to round down to the final statement.
Yeah, round. But sometimes when you're doing the trig ones, you're going to get like a bunch of crazy decimal places, right? Just write down whatever is in your final box there, the bunch of decimals. Okay, but this one you can see it's kind of heading to 320. Do you know what I mean? And the last one here, you can see it was heading towards 6. But sometimes it's hard to see. If you're ever not sure, just write down whatever's in your last thing there. You know what I mean by that?
Yeah.
That way you won't get it wrong. Okay? And that's all there is to instantaneous rates of change. Average rate of change, you do the slope formula once. Instantaneous rate of change, you're doing it 3 times. You're looking at this final answer, and you're answering the question. Okay? That's essentially the guide. The only difference is in the coming days, we're going to look at slopes of secant lines and tangent lines, but you're going to see it's essentially the exact same stuff. Okay. So I'll save this as always.